So in the last lecture, we developed the equivalence circuit, which is just representing these two characteristics equation of the transformer. But one point was not represented. That is the magnetizations, how magnetization is occurring in the transformer. We discussed in our earlier lecture that we can represent the magnetization current as if current is passing through an inductor and magnetic loss due to the magnetic flux by a resistance which is connected parallel to it. So if I incorporated that inside this, so I can put here this thing. This is your magnetizing coil and this is your resistance, which will be accounting for this your magnetic loss. The resistance is called RC, core loss resistance, and this is called XM, magnetizing reactance. So whatever current will be passing I0 through it, magnetizing current will be there IEM, and there will be core loss current, that is IC. So this is the complete magnetizing equivalence circuit of the transformer, accounting both its primary, secondary and magnetization characteristics of the transformer. Now what you want, that instead of these two loops, if there is one loop, then solving the circuit becomes much easier. So this is a coupled circuit, magnetically coupled circuit, electrically isolated but magnetically coupled circuit. If this coupling system we can delete, then this circuit will be much easier. But how to delete it? Here this voltage is E1, here this voltage is E2. It is being produced by the same flux, but as number of coils, number of turns in the primary is higher, E1 is higher than E2. These two, if it was like this, that E1 and E2 are equal, then these two voltages would have been equal. I could have joined these two branches and these coils would have been omitted, deleted completely, because it is not contributing then anything, voltages are being equal. But how to make the secondary voltage equal? We know that E1 by E2 is equal to N1 by N2. So if I make same number of turns, that means here number of turns is N1, here number of turns is N2. So if I replace this secondary coil by another coil whose number of turns is same as primary, that means number of turns is N1, then these two coils will have the same voltage. So what we can do is, we can just change this coil. Let us just imagine we change the same coil with the same number of turns N1. So what will happen then? Here the voltage is E1, here also voltage will be E1. So these two voltages, here voltage, here voltage, voltage here, both are same. As soon as the voltages are same, we can join these two coils, because it is having equipotential. In this at all points, potentials are same. Here also potential is same, I can join. But if I join these two, I am replacing this coil by N1. But how it will represent the actual situation? So what we are getting, my voltage was E2 in the secondary with N2 number of turns. Now I have replaced it by another coil having N1 number of turns. So how much voltage I will be getting? E1 into N1 by N2. That means E2, N1 by N2 is alpha. This we will be calling it E2 dash. That means now modified voltage will be, here voltage will be now E2 dash. But what is E2 dash? You know, E1 by E2 is equal to N1 by N2. So E1 is equal to N1 by N2 into E2. That means alpha into E2, same. So this is equal nothing but E1. So these two voltages will be equal as soon as I am replacing it same number of turns. And when it will be same number of turns, these two will have same voltage. So I can omit this transformer, that means this transformation coil, magnetic coupling between these two can be totally omitted. But that will change the current in the circuit. Now you see the condition of the circuit. This current, which was I1 current is here. Here I0 is going, say here IB is the current. Now the same current will be passing through the primary and the secondary side. So this will create changes in the I1. That is not permitted. We will have to keep this I1 same by doing these changes. So what you can do, we can change this resistance R2 and X2 in such a way that total impedance of the circuit, which is actually V1 is experiencing the total impedance of the circuit and driving the current, that should remain constant. That means our resistance should be such that total resistive loss in the circuit, this secondary side, should remain same. That means with this, originally my resistive loss was I2 into R2. Now it has become I2 dash, I2 square R2. Now it has become I2 dash square R2 dash. So how much will be R2 dash? R2 dash will be equal to R2 into I2 by I1, I2 dash whole square. But what is I2 dash? I2 dash is nothing but I1. So R2 into I2 by I1 into square. What is I2 by I1? I2 by I1 is your turns ratio. So it is alpha square. So your resistance, this resistance should be R2 dash. This resistance should be R2 dash, R2 into alpha square. So the resistance, we should make it R2 by alpha square. That is called R2 dash. Now how much should be the X2? X2 value. How much should be the X2 value? The actually percentage, how much percentage of the voltage was available, was there, inductive voltage drop, how much it was percentage of that voltage. It should be same percentage now also. That means I can say inductive voltage drop was I2 into X2, voltage was E2. Now my change circumstances, it had become I2 dash, it will be X2 dash, I'll have to change it to, and my voltage will be E2 dash, that means E1. So my X2 dash will be X2 into I2 by I1 into E1 dash by E2 dash. E1 dash by E2. So I can say very well, I2 by I1 is again alpha, E1 dash E2, it is E2 dash. E2 dash by E2 is again alpha. So again it is becoming X2 into alpha square. So now it will become X2 dash will be X2 into alpha square. So that means I am bringing these secondary resistance and leakage reactance to the primary side with these changes R2 dash and X2 dash. This is called resistance of the secondary referred to the primary, and this is called reactance, leakage reactance of the secondary referred to primary. If we can refer the things in the secondary side also, then the primary side resistance and leakage reactance is to be referred, and you can very well find it has to be divided by the turns ratio square, R1 by turns ratio square, X1 by turns ratio square. If you do, it will be referred there. So this is actually actual complete equivalent circuit of the transformer. Now for different types of operation, that means in the no load condition, in the load conditions, we can further simplify this equivalent circuit without compromising any accuracy or any sorts of deficiency in representing the transformer. So in the next lecture, we'll be carry on this type of equivalent circuit modeling of the transformer in different loading conditions.